Okay, so welcome everyone. Welcome to Harvard CMSA Quantum Matter in Math Physics seminar. We are very delighted to invite Junkai from Harvard here. He will be speaking about his work and join work with collaborators on exact many-body ground states from decomposition of ideal higher Chern bands, applications to chirally twisted graphene multilayers. Let me remind the audience, please feel free to ask questions and interact with Junkai during his seminar, and let's directly welcome Junkai. Please, so yours.
Thank you. Thank you for the kind introduction. I'm Junkai Dong. I'm a second-year graduate student in Professor Ashwin Vishwanatha's group, and today I'm happy to introduce to you our new work, Exact Many-Body Ground States from Decomposition of Ideal Higher Chern bands. So here is an overview of the problem. The interacting electronic system is very hard to study, as we all know. The strong interactions preclude a Landau Fermi liquid description of the system, and you no longer have the convenient electron-like quasi-particles to work with. So what do? When the underlying band is flat and non-topological, you may linearize and construct localized Wannier orbitals and build a Hubbard model out of it. And this gives you a theoretical tool to give analytic statements on the interacting problem. However, when the underlying band is topological, this description is no longer valid because your Wannier orbitals will have long tails. What do? So however, although the problem is very hard, it is very rich, as we know two realistic examples that generate very interesting phases. On the left, we have the fractional quantum Hall effect, in which the underlying band is a lowest Landau level. When you fractionally fill these a lowest Landau level, you get the fractional quantum Hall effect. These are topological orders. They have fractionalized excitations and ions. They carry fractional charge and have mutual fractional statistics. On the right, we have the twisted bilayer graphene. Not only do they exhibit correlated phenomena such as mod insulators and superconductors, they also have cousins of these fractional quantum Hall states called fractional Chern insulator states. And the underlying band is also topological. So the problem is very hard, and analytic progress is also very difficult, but the problem is very rich. In this work, we will present some analytic results in interacting higher Chern bands, meaning Chern bands with higher Chern numbers. Using a tool called quantum geometry, we may make we can use a single particle description of the band to generate many-body exact statements. Firstly, we consider an ideal Chern band with higher Chern number and decompose it into many ideal Chern bands with Chern number 1. Each of these ideal Chern bands basically function as a lowest Landau level. And then we may use these decomposed Chern bands to construct many-body exact ground states. There are two classes of them. The first of them is a class of topological charge density waves, which we understand as generalized ferromagnets. And then we study the excitations upon these ferromagnets. Some of them are more exotic, which are the skyrmions of these ferromagnets. And another class are topological orders. These are analytic fractional Chern insulator states through the vortex attachment procedure. Again, please feel to interrupt and ask questions during the talk. So we will basically follow what we just described. We'll first introduce what is quantum geometry, and importantly, what is ideal quantum geometry. Then we will march on to the single particle description and describe the decomposition of ideal Chern bands, and then construct many-body ground states out of them. So where does quantum geometry emerge? It comes from the study of fractional Chern insulators. Basically, people have been searching for bands that host fractional Chern insulators. So one band that we know that has these fractional Chern insulator states is the lowest Landau level. If you make your band as similar as the Landau level, you will be sure to get fractional Chern insulator states. So what are the key ingredients of the lowest Landau level that you should mimic? Firstly, the lowest Landau level has completely flat dispersion. And as we have said, the flat dispersion is very important because strong dispersions make your interactions look weak, and the interactions will simply renormalize the dispersions. So from now on, we will take our bands to be completely flat. Apart from the flat dispersion, we also have the single particle wave functions, which are known as the block wave functions. They enter the Hamiltonian through the density-density interaction. In particular, they come in the form of these overlaps, which are known as form factors. These form factors exactly determine both the topology of the band, meaning its Berry curvature, and how the band looks in real space, its real space profile. Importantly, these form factors completely determine the many-body problem. And if you have these form factors, you can put them onto a computer and run exact diagonalization. And that will tell you whether your ground state will be a topologically trivial state, such as the charge density wave, or a topological order, such as the fractional Chern insulator. However, this is simply too much information, meaning you have one periodic function at every momentum point. You have a gazillion degrees of freedom you have control over. So what is the key ingredient in these block wave functions that tells you a band is good for fractional Chern insulators? Recently, people have found that the key ingredient is called quantum geometry. Importantly, the quantum geometry lets you distinguish the difference between the lowest Landau level and the 50th Landau level. Note that both bands are completely flat. They have completely flat Berry curvature too. However, the phenomenology of their fractionally filled states are completely different. In the 0th Landau level, for example, you get the 1/3 Laplace state, which is a fractional quantum Hall state. However, at the 50th Landau level, you usually get a charge density wave. The key difference between those two bands is precisely their quantum geometry. So how does quantum geometry make lowest Landau so great that it gives fractional Chern insulator ground states? So there is a condition in quantum geometry that is called the ideal quantum geometry condition. And we call bands that satisfy the ideal quantum geometry condition ideal bands. Ideal bands are good in that they satisfy a vortex attachment property. This is saying that if you take a wave function psi from your band, you can multiply this wave function by z, which is x plus iy, to your wave function without kicking yourself out of your band. How is this good? If you take a non-ideal band, multiplying by z will usually kick you out from the band, and you will go to some band with very high energy. So, but however, when you have an ideal band, multiplying by z doesn't cost you any kinetic energy. This applies to arbitrary analytic functions of z and works for many body states as well. And as we will see, this vortexability, meaning ability to attach a vortex, has important many body implications. Recall that the Laplace state is obtained by attaching 2s vortices to each electron from the lowest Landau level Slater determinant. Now, the lowest Landau level is an ideal state, ideal band. Now, if we replace this lowest Landau level for any ideal band, the resulting vortex-attached fractional Chern insulator will still pay very low kinetic energy. Now, if you look at this factor more closely, you notice that it's actually this vortex attachment factor, zi minus zj to the 2s, actually helps you with the interactions as well. When two electrons get close to each other, this factor suppresses the probability density, and thus it pays very little energy to short-range interactions. And in particular, if you use the pseudo-potential expansion of interactions and you cut the expansion off at some power, you will actually pay zero energy. This vortexability property also has a manifestation in momentum space. It is equivalent to the ability to choose a holomorphic gauge in momentum space for your block wave functions U. Your block wave functions U will only depend on the combination kx plus iky. This is very important because you can now apply all sorts of tricks of complex analysis to your single particle wave function. So this is a lightning review of ideal quantum geometry. Please ask questions if you have any right now. All right, now that we have established the fact that ideal bands are great and they give rise to, yes.
What do you try to show on this right-hand side figures layer?
Okay, the right-hand side is showing the following. The center band, red band, is an ideal band. And it's saying that if you multiply wave functions, the wave function psi by z, it stays within the band, which is shown by the red arrow on the right. Normally, you will also have a non-trivial matrix element that kicks you out of the band, which is the purple layer on the right. But this does not happen for ideal bands. All right. Now that we have established the fact that ideal bands are great and they give you fractional Chern insulator ground states, do they exist outside of the vacuum? What are some examples of ideal bands? The simplest example of ideal bands with Chern number 1 is the lowest Landau level. In particular, if you impose a condition that a band is both ideal and has uniform Baire curvature, you get the lowest Landau level. Interestingly, an ideal band also arises out of the chiral model of magic angle twisted bilayer graphene. This model is obtained from the realistic twisted bilayer graphene model by ignoring certain interlayer hoppings. Importantly, these ideal bands from the chiral model has been important in understanding the fractional Chern insulators in such systems. Because we have the momentum space holomorphic gauge to work with, the wave functions of any arbitrary ideal Chern number 1 band is completely classified. And they're shown to be completely equivalent to the lowest Landau level wave functions of Dirac fermions in a homogeneous field. Concretely speaking, take any ideal Chern 1 band. It can be decomposed into a product of a lowest Landau level wave function and a spinner, in which the magnitude of spinner is spatially varying and describes the profile of the inhomogeneous field. Apart from ideal bands with Chern number 1, you can also have ideal bands with larger than 1 Chern number. The first example is multicomponent lowest Landau level, which basically means that you take several layers of lowest Landau level and stack them on top of each other and consider them as a whole system. You also have the chiral graphene multilayers. These are formed by taking firstly m layers of chirally stacked graphene. By that I mean that the graphene layers are untwisted with respect to each other and they have consecutive AB or BA stacking. You take m chirally stacked graphene layers and you take another set of n chirally stacked graphene layers, and then you twist them. When the twist angle is tuned to exactly the magic angle of chiral TBG, and you ignore certain interlayer hoppings similar to the assumptions you make for chiral TBG, you generate flat ideal Chern bands with higher Chern number. These are physically realistic systems. these graphene multilayers have actually been manufactured in lab in the form of monobi, which is a monolayer bilayer, where n equals 1, m equals 2, and bi-bi, which is double bilayer, where n equals 2, m equals 2. In both of these cases, the higher Chern number, the Chern number of the ideal band has Chern number 2. However, generally you can tune the Chern number by varying the number of layers n and n. Is there some echo from somebody? Oh, never mind. Thank you.
I'm mute.
All right. Thank you. Anyway, thanks. The ideal higher Chern band from this model is actually not equivalent to the simple case where you have several layers of lowest Landau level. And this setup will be our primary example and motivation. So to summarize, in the past section, I have described to you a tool that describes single particle properties of the band that have many body implications. This tool is called ideal quantum geometry. In real space, it has the vortexability property, which says that if you take a wave function from this ideal band and you attach a vortex z to it, you will still stay in the band. In momentum space, this is equivalent to the ability to choose a holomorphic gauge. This vortexability property then gives us an analytic recipe for fractional Chern insulator ground states. If you have a flat, ideal Chern band under short-range interaction, we can guarantee that the ground state will be a fractional Chern insulator, and we can even cook up analytic ansatz for the fractional Chern insulator state. Any questions before we move on from ideal quantum geometry?
Maybe let me add something. So usually this fractional translator, you may be just able to write down some lattice model to construct such the low energy have the this FCI.
Mm-hmm.
But here you are not going to present the lattice model.
No. In fact, you're completely right. You're saying that usually you say that you take some lattice model, say you have a half-stature model, and then you throw interactions and you do all of this numerically. In particular, this is an analytic statement that is totally beyond the numerical limit. And no, so there's no lattice model in these bands, and we just assume that we just assume an ideal band from the start. Basically, we do not tell you where the ideal band comes from. Although from the examples of the ideal band, you can believe me that these ideal bands do come out from realistic problems.
Maybe I can add something, which is that I think when Juven says lattice model, there are two things you could take that to mean. One, you could mean some UV description of the system that doesn't have continuous translation symmetry, or you could mean a literal lattice model where the wave functions are delta function localized to atomic sites. And the first perspective is a bit more general. It allows the wave functions to have some spread in real space and a bit more realistic as well. And that's actually where the ideal quantum geometry emerges in these graphene multilayers. So they're continuum models, but they have they don't have any, they have a lattice translation symmetry.
Yeah, thanks, Patrick. All right.
Hi.
Yes.
In the vortexability condition, why there is a projection operator? Because when we multiply z, we also lie in the same Landau level. That means z psi equal to p z psi. So what is p? Is this projection operator?
Yes. So basically, you're saying that if this is the lowest Landau level, I multiply it by z, I still stay within the lowest Landau level. I do not need to apply the projection operator. Is that what you're saying?
Yeah.
Well, that is exactly the special property of the lowest Landau level, right? If you multiply a wave function in the first Landau level by z, you will, get kicked out of the first Landau level. You will no longer stay in the first Landau level. This is exactly why the first Landau level is different from the lowest Landau level, and why the lowest Landau level is special. Does that make sense?
Yeah, but the psi here is lowest Landau level, right?
Oh, no. It's an ideal band. It's a generalization from the lowest Landau level.
Okay, thanks.
Right. Thank you. All right.
But let me make sure. So does it help to also write on a lattice model? For example, there could be just some simple model of hopping of a nearest neighbor, next nearest neighbor, and there could be some flux straight into those, maybe some unicell or some of the larger unicell, and those are the conventional way to write on some FCI or just even Chern insulator. And here you present a different way. Are there some relation to them, or are you also able to relate to some lattice model in the end?
In the end, these are so. Let me reinterpret the problem in saying, am I able to get ideal bands out of lattice models? And the answer is yes, in which you take the Kapit-Mueller model. These are lattice hopping models with some phase and some flux, and the low-lying band is exactly an ideal band in that case. So maybe if you take the Kapit-Mueller model and interactions, this satisfies your. This is a model you want, basically. Yeah. Thanks for the question. All right, now that we know something about ideal quantum geometry, we can move on to study higher ideal Chern bands. As we have said, the ideal bands with Chern number 1 are basically lowest Landau levels. Now, so the Chern 1 has been completely classified. We need to move on to higher Chern numbers to say something different. In the first place, why are higher Chern bands interesting? They're interesting because they have a rich phenomenology, a wide variety of fractional Chern insulator states, both of abelian character and non-abelian character. And within those abelian fractional Chern insulator states, there are also non-abelian defects. These defects are lattice dislocations, and when they wind around each other, they effectively create a hole out of your real space manifold. They effectively increase the genus of your real space manifold. And this is why they are also called genons. So what is the simplest example of a higher Chern band? As we will present here, we will reinterpret a quantum Hall bilayer, which, as we will see, has Chern number 2 as a Chern band with Chern number 2. So here is a quantum Hall bilayer. You have the 2 layers, top layer, color as red, bottom layer, color as blue. How do we understand this system? We can understand it via the following. We take a unit cell generated by C1 and C2, which encloses flux 2 pi. And given the flux enclosed, the magnetic translations commute with each other. Using these commuting translations, you can define your block states, and you get 2 sets of block states, which means that you have 2 bands corresponding to the top layer lowest Landau level and the bottom layer lowest Landau level. And each of the bands, as you know, has Chern number 1. Now, there's an explicit flavor symmetry SU2 that rotates you between the layers. Now, here's another way to view the problem. Let's take another unit cell, a smaller unit cell, generated by A1 and A2 with flux only pi. Now, the magnetic translations will no longer commute. You get a minus sign from the pi flux. So you're no longer able to define the block states using these magnetic translations. However, you can still define commuting translations using a combination of the layer rotations and the magnetic translations. So notice that the layer rotations tau x and tau z don't commute. The magnetic translations A1, Tmac A1 and A2 don't commute, but the combinations of them will commute. Using these two commuting translations, you can only define one set of block states. This will be a single band with Chern number 2. Now, if you are simply handed the Chern number 2 basis, the flavor symmetry will be hidden in the problem because effectively you have used up all your SU2 rotations when you define the fundamental translations of the band. One interesting thing that we observe in this simple reinterpretation is that Chern-1 ferromagnets become charge density waves. That is, let's take the simplest ferromagnet. You completely polarize and fill the top layer. So the red layer is completely filled. The blue layer is completely unfilled. Now this is a tau Z ferromagnet. Basically, all the spins are pointing up, and thus it will not be symmetric under TA1 because tau x wants to flip all the spins to the bottom layer, but it will be symmetric under TA2. So the all spin pointing up ferromagnet breaks TA1 translations, but does not break TA2 translation. Importantly, this is an insight that we will use again and again in the following contents of the talk, that Chern-1 ferromagnets become charge density waves under Chern-2 translations. So now that we have two descriptions of the same system, we want to be able to translate back and forth between the interpretations. Now that we have gone from the Chern-1 description to the Chern-2 description, how do we translate back? Well, you might say that you look at the unit cell. This Chern-2 unit cell encloses flux pi, where the Chern-1 unit cell encloses flux 2 pi. If we simply enlarge the unit cell in the A1 direction by 2 times, we double the unit cell, can we recover all the description of the problem? It turns out that if you square the A1 translation, but keep the A2 translation invariant, there will still be some remaining SU2 translation in the problem. And thus, you will not get a momentum diagonal SU2 rotation between the two bands. This means that the layers are momentum shifted. If you take the tau z eigenstates, the translations acting on them will give you an additional minus sign. This is like them sitting at momentum shifted by pi. To recover a momentum diagonal SU2 rotation between the bands, we need to actually quadruple the unit cell. We need to double the unit cell in both the A1 and the A2 translations and the A2 directions to get rid of all the SU2 rotations in the translations. And from a momentum space point of view, this is saying that notice that the original complicated translation operators are defined as flavor symmetry rotations, tau, and magnetic translations, Tmac. Now that we start from the Chern-2 basis, we have natural access to the translation operators. So we need to figure out what are the magnetic translations in the Chern-2 basis. Note that the magnetic translations do not commute with the normal translations. Particularly, Tmac A1 does not commute with TA2. And thus, the magnetic translations actually shift translation eigenvalues. This means that the magnetic translations are momentum translations. And note that the momentum translations are usually notoriously gauge dependent on the momentum space gauge. So you have to fix a gauge to talk about momentum translations. And thus, the flavor symmetry is actually a combination of momentum space translations and real space translations. If you calculate what the momentum translations are for tau x and tau z, you notice that they respectively shift the momentum by g1/2 and g2/2. These are basically like pi0 and 0 pi. Now, normally, if you use a doubled unit cell, one of these will not be a reciprocal lattice factor. You're effectively shifting momentum, which is why you don't have a momentum preserving SU2 rotation. Now, if you quadruple your unit cell, both of these will become new reciprocal lattice factors, and thus you recover a momentum diagonal flavor action. This is in correspondence with the fact that our new double translations will not have any SU2 rotation constant. So let's just recap what we have learned from the quantum Hall bilayer. From the quantum Hall bilayer, we learned that once you have the Chern 2 description of the system, you need to quadruple the unit cell. You double the unit cell in both directions to recover a momentum diagonal flavor symmetry rotation. And this flavor symmetry is actually a combination of momentum space translations and real space translations. Furthermore, Chern 1 ferromagnets become charge density waves under Chern 2 translations. Equipped with the knowledge from the quantum Hall bilayer, we can move on to study generic higher Chern bands. Let's set up the problem by defining the lattice vectors to be A1 and A2, and the corresponding reciprocal lattice vectors to be G1 and G2. In order to facilitate the description of the many-body problem, we will also take the band to have ideal quantum geometry. And as we know, this is equivalent to our ability to pick a holomorphic gauge in K-space. These block wave functions U only depend on the combination Kx plus IKY, which we will call K from now on. However, simply saying that your momentum space gauge is holomorphic is not enough to completely fix a gauge, because I can multiply this wave function by an arbitrary analytic function in K. So we need to impose additional constraints. These are called boundary conditions. They basically tell you what happens when you translate your wave functions by a reciprocal lattice factor. In particular, we impose these canonical boundary conditions. In particular, it imposes the condition that the band does nothing when we translate by G2, and the wave functions get an exponential factor when you translate by G1. These boundary conditions contain information about the topology of the band. In particular, if you calculate the total phase winding accumulated through translations by these boundary conditions, it is related to the Chern number. We must caution the audience that the holomorphic gauge is a pretty dangerous gauge to use, in the sense that your wave functions psi k in this gauge is not normalized to unity. And if it were normalized to unity, it would be pretty boring. This is known because the holomorphic functions, non-trivial holomorphic functions, are not bounded. And if they are bounded, they are basically just a constant. So let's decompose a Chern number 2 band, Chern number 2 ideal band, into two Chern number 1 ideal bands with some SU2 action that rotates between them. Let's start with the band psi k, which has Chern number 2 and lives in the Brillouin zone G1 and G2. These are shown by the black dots here. one simple attempt to create two bands out of this one band is by breaking the translation in the A1 direction. This shrinks the Brillouin zone in the G1 direction, and you basically fold your Brillouin zone. You get two foliations and two bands. You have the band psi k on one foliation, which is shown back, and another foliation with the band k plus G1/2, which are shown in white. Importantly, these two bands are not independent of each other, because if I translate by the reciprocal lattice factor G1/2, they transform into each other. Formally speaking, this is saying that the boundary conditions corresponding to these two bands are not diagonal. Now, non-diagonal boundary conditions are nasty. They're not independent bands, but we want independent bands. So we need to holomorphically diagonalize the boundary conditions. We form some holomorphic linear combinations of the black and white bands to form new bands phi0 and phi1, which are shown in blue and red here. These two bands are holomorphic linear combinations, so that, and as we know, products of holomorphic functions are still holomorphic. So both of these two bands, phi0 and phi1, are still ideal. Importantly, they will have diagonal but different boundary conditions. Notice that the two boundary conditions after the diagonalization process are related by momentum translations. This is saying that phi1k have the same boundary conditions as phi0 k plus G2/2. Now, if you have two bands with the same boundary conditions, you can mix them and still get independent bands. If you have two bands with different boundary conditions, you're not allowed to mix them, because you will generally translate to some different band when you translate by a reciprocal lattice factor. So we can form arbitrary linear combinations of these two bands, which we will now call phi tilde 0, which is the momentum shifted phi0 band, and the phi tilde 1 band, which is the momentum unshifted phi1 band. These linear combinations of ideal bands form a representation of the SU2, because you can take arbitrary linear combinations, and we'll call this the generators of these SU2 tau i's. Note that these tau i's are generally non-unitary. How do you see that? For example, you just take tau x. Tau x should change, should map phi tilde 1 to phi tilde 0. Now, phi tilde 1 and phi tilde 0 will usually have vastly different norms. So in an orthonormal basis, these taus would not be unitary. However, the algebra that they obey will be completely equivalent to the usual SU2 that you know. It's just that the inner products will be slightly different. Now, since you're combining degrees of freedom at different momenta, you should fold your Brillouin zone again. And right now, you have 4 degrees of freedom at each momentum in a Brillouin zone generated by Gy/2 and G2/2. And if you recall, this is equivalent to the quantum Hall binary case, in which you enlarge the unit cell in both the A1 direction and the A2 direction. So this is the quadruple unit cell and quarter Brillouin zone. You have 4 degrees of freedom. You have the phi tilde 0s and the phi tilde 1s, and their momentum shifted patterns. Note that, again, the degrees of freedom in this spinner are not independent of each other. For example, the first component, phi tilde 0k, is not independent from the third component, because they're related by a shift of the reciprocal lattice factor G2/2. The physical meaning of this independence is that you cannot say that I want to fill the first component of the band phi tilde k. You have to fill both of them for it to make sense. And when you fill both of them, say the first layer and the third layer, it's like you're fully filling all the bands with upspin. And thus it is a ferromagnet. And as we promised, the ferromagnets will break translations, as we show below. In this spinor representation, the translations and magnetic translations have this form. The translations fractionalize into a product of SU2 rotations, which rotate between the 1, 0, and 1 indices, and another SU2 rotation, which rotates the indices k and k plus g2 over 2. So this mu SU2 rotation shifts momentum. And thus, heuristically, and we make it more precise in the paper, that this mu rotation is actually equivalent to a magnetic translation, because magnetic translations shift momentum. And thus, since a band fills both of these states, the mu rotations do not do anything to them, and translations basically act as rotations of the ferromagnets. And thus, if you take a general ferromagnet, these rotations will not leave the ferromagnet invariant and will break translations. And as we see, that the flavor symmetry can be expressed as a combination of momentum translations, which are quote unquote magnetic translations, and normal translations. To summarize, with envisioning towards the many-body problem, we have performed an ideality-preserving decomposition. We took an ideal band with Chern number 2 and broke it down to 2 ideal bands with Chern number 1 by breaking translation symmetry in the A1 direction. These 2 ideal bands, because they have Chern number 1, are basically modified lowest Landau levels. And we notice that the 2 ideal bands, when shifted by some momentum, have the same boundary conditions. We folded the Brillouin-Zone gain and constructed an explicit momentum diagonal SU2 action between using this big spinor phi tilde. Importantly, the SU2 action is a combination of momentum space and real space translations, and it will become emergent symmetry in some situations. We note that the above procedure not only works for the case Chern number 2, but also works for arbitrary Chern number as well. So do we have any questions before we move on to the many-body problem?
I have a question.
Yes.
When you say it works for arbitrary Chern number, do you need to does the same quadrupling of the unit cell work for arbitrary Chern number or something else?
No. Say you have Chern number C, then you need to do a C enlargement. Basically, you need to take your unit cells to be CA1 times CA2.
Got it. Thanks.
Yeah. Any other questions? All right. So now that we have completely solved the single particle problem, we can now move on to the many-body problem. In particular, we will find topological charge density wave ground states and various fractional Chern insulator ground states. And we have analytic ansatz for all of the for both of these cases. So let's study the first case. The physical setup is you take an ideal band with Chern number 2 and you half fill the system with contact interaction delta R minus R and minus RJ. This means that when the electrons sit on top of each other, you pay some energy. And if the electrons are sitting apart, you don't pay any energy. Importantly, this contact interaction is positive definite, meaning that all of its eigenvalues are larger than or equal to 0, which means that its 0 modes are the ground states. So to find the ground states of this problem, you need to find the 0 modes. Let's present to you one set of these 0 modes. which are called generalized quantum Hall ferromagnets. The generalized quantum Hall ferromagnets is defined as fully filling an ideal band with Chern number 1. The simplest example of which is that you take a lowest Landau level and completely spin polarize it, which is why it's called a generalized quantum Hall ferromagnet. Now, why does this state have zero energy under contact interaction? Recall that the wave function of an arbitrary ideal band with Chern number 1 can be decomposed as the product of lowest Landau level wave function and the spinner. Importantly, the spinner does not depend on the momentum, and Pauli blocking will give you a many-body zero when 2 electrons coincide. If the spinner does depend on the momentum, let's say you have the spinner pointing up at some momentum and the spinner pointing down at some other momentum, these two different momenta wave functions can sit on top of each other, and you can imagine that you will pay some energy to the contact interaction. However, when the spinner does not depend on the momentum, this state will pay zero energy. And thus, generalized quantum Hall ferromagnets become exact ground states under the contact interaction. The question right now is, of course, where do we find Chern number 1 ideal bands to fill? Well, we know where to find Chern number 1 ideal bands. We just decomposed our Chern number 2 ideal band into 2 Chern 1 ideal bands. And we know that by linearly combining these 2 Chern number 1 ideal bands, we can generate more Chern number 1 ideal bands. And for example, we can take one arbitrary linear combination of 2 these ideal bands and get another Chern number 1 ideal band. Let's fully fill one of these arbitrary linear combinations. And basically, in this case, we get ferromagnets. And as you recall, all of these Chern 1 ferromagnets break some sort of Chern 2 translations. And thus, they become charged density waves. So your many-body ground state manifold will be a set of a continuous set of topological charge density waves, which have this ferromagnetic order. In particular, if you project yourself to the many-body ground state manifold, you will find that the SU2 action, which rotates you between the ferromagnets, become an emergent symmetry of this manifold. It is not a symmetry of each state, particularly. And using this SU2 symmetry, you can analytically predict the ground state degeneracy. In particular, each electron functions as some spin half, and since you want a ferromagnet, you want to take the all-symmetric representation of the spin half, and its dimension is exactly Ne+1. We can numerically verify that this ground state degeneracy is correct by taking the Chern number 2 ideal band from the monobi graphene. And we use contact interaction and half over the system with 12 electrons. And in particular, we get a ground state degeneracy of 13. Although you can only see 4 dots, they all have completely zero energy, and they basically sit on top of each other. And as we emphasize here, the ground state manifold is generated by ferromagnetic topological charge density waves. Well, that's cool. Why don't we see some realistic? Why don't we see some pictures of how these charge density waves look like? So basically, from now on, we will take a monobi graphene, and we look at its Chern number 2 ideal band, and we look at how the ferromagnets from this Chern 2 ideal band look like. Now, as we have said, for ferromagnets, translations act as ferromagnetic rotations. And thus, if you take an eigenstate of that ferromagnetic rotation, basically you take an eigenstate of x, y, or z, it will be also an eigenstate of some sort of TA1, TA2, or TA3. What this is the charge density of an X ferromagnet. As you can see, it is symmetric under the unit cell of 2A1 by 2A2. On the other hand, it has also the symmetry of translation by A1, as shown in the black arrow here. As you can see, it breaks translation by A2 and A3. Let's take another ferromagnet, that is the Z ferromagnet. And as you can see, it is symmetric under A2 translation, but breaks A1 and A3 translations. The X ferromagnet looks exactly the same like the Z ferromagnet, rotated by 120 degrees, because this graphene model has C3 rotation symmetry. Now, let's take a moment to appreciate the fact that we have a continuous manifold of charge density waves. If I tell you that you half fill your system and you get charge density wave ground state, you will say to me, yeah, sure, let's break translation symmetry. Let's take a 1/2 unit cell and construct charge density waves. Basically, you get strike phases. And the strike phases are exactly these X, Y, and Z ferromagnets. Now, the peculiar thing is that there are additional charge density waves that interpolate between these strike phases. And more importantly, they are all ground states under contact interaction. Particularly, let's plot one of these general ferromagnets that does not point in X, Y, or Z direction. This is the 111 ferromagnet. It points in the diagonal direction, and it has C3 rotational symmetry when around the origin. And thus, we can give a block sphere interpretation to our ferromagnetic ground states, which are, importantly, topological charge density waves.
Maybe let me add something simple, just to clarify. I guess you say this ground state manifold is generated by ferromagnetic topological charge density wave.
Yeah.
And ferromagnetic here breaks time reversal, no? Break time reversal.
Good point. It is slightly different from the ferromagnetic order that you naively describe. Because usually you're thinking about spins, real spins, right? And these real spins have some non-trivial time reversal symmetry action. However, these are pseudospins. Pseudospins themselves don't break time reversal. However, the origin from the time reversal symmetry, some symmetry breaking, comes from the fact that each of these bands are topological. So basically, you are filling one of the lowest Landau levels, and the lowest Landau level, because it has Chern number 1, it breaks time reversal symmetry. It's not coming from the fact that they are pseudo-spin polarized. Am I being clear here? It's like saying in graphene, let's say you have a lowest Landau level on the A side and a lowest Landau level on the B side, and you completely fill the lowest Landau level from the A side. Now, simply by polarizing the sublattice, you do not break time reversal symmetry. However, since it is a lowest Landau level, it breaks time reversal symmetry.
Okay, thanks. And the charge density wave breaks translation symmetry.
Yes.
Do you also, the full ferromagnetic topological charge density wave also breaks other, like a charge U1 or any other symmetry?
Does not break charge U1. I'm not sure if there's any other symmetry from the most general setting of the problem. Yeah.
And the topological here, topological CDW, just to emphasize, there's a non-trivial Chern number.
Yes, because you're completely filling one ideal Chern 1 band.
Okay, thanks. Thank you.
Great, thank you. Thank you. And thus, we can give basically a block sphere interpretation of our topological charge density waves. Each point on the sphere correspond to a ferromagnet, which is a topological charge density waves, where this Bloch sphere intersects with the Cartesian axis. You get X, Y, and Z ferromagnets, which are shown by the yellow dots. These yellow dot ferromagnets are the stripe phases. Whereas you also have these red arrows. These red arrows preserve the C3 rotational symmetry. Translations and rotations in real space will become rotations on the Bloch sphere. Basically, their actions on the ferromagnets can be projected onto the Bloch sphere. Translations become rotations around the XYZ axes by pi. And these are basically the tau 1, tau 2, and tau 3s. C3 rotations, however, are rotations around the red arrows by 2 pi over 3. This is a completely general statement for arbitrary C3 symmetric ideal Chern band. Similar Bloch sphere pictures can be drawn for other rotational symmetries as well. For example, the C4 rotational symmetry. Now that we have established that we have ferromagnetic ground states, we can consider the excitations upon these ferromagnets. You can, of course, have dot-like electron excitations, but also you have these skyrmion excitations. Skyrmions are topological textures of spin. And importantly, they carry charge in the topological bands. Its charge will be directly proportional to the Chern number of the underlying band. And here I plot a sample texture of a skyrmion. You can find that it winds exactly once around the Brillouin zone as you go over the entire plane. Because it can be very extended, it often has lower energy than the barrier electron under longer range interactions, like Coulomb interactions. So what do skyrmions look like in our cases? In our cases, pseudospin skyrmions are basically windings of charge density patterns. Here, I plot the charge density profile of a sample skyrmion. In the middle of it, it has some C3 symmetric pattern. As you generally go away from the center, the charge density pattern starts to wind around. And it winds around again as you go further, and before it goes into some uniform charge density pattern at infinity. These charge density profiles are can be very easily probed by local probes such as the SDM because of the large density variations as shown in the left here. So much for ferromagnets. Let's move on to fractional Chern insulators in this case. As we have said, that these ideal Chern bands are especially good for fractional Chern insulators because we can construct vortex-attached FEI trial states in these ideal bands. Basically, the inspiration comes from the Laughlin state, in which you attach 2s vortices to an ideal band, to a general ideal band. And we ask the question, what is the resulting fractional Chern insulator state? In particular, we care about the topological character and the filling at which the fractional Chern insulator occurs, and other properties. However, it is unclear at this point. One statement that we can make at this point is that the translation properties of the fractional Chern insulators descend from the Slater determinant that we start with. Basically, if the Slater determinant is translation symmetric, the fractional Chern insulator will also be translation symmetric. If the Slater determinant is translation broken, the fractional Chern insulator will also be translation broken. Now, let us look at the first case, which is translation symmetric fractional Chern insulator states. You take a translation symmetric Slater determinant, which we take to be a fully filled ideal Chern band, and It's a pseudo-spin singlet, so it does not break translation symmetry. This is equivalent to fully filling two ideal Chern 1 band from the decomposition. In particular, you can see that the fully filled Chern 2 band has almost the same wave function as the quantum Hall bilayer, except for this complicated spinner here, which arises from the microscopics of the band. After you attach the vortices, you notice that this will be equivalent to the Halperin 2s plus 1, 2s plus 1, 2s state. Basically, this tells us that the microscopics of the band, the spinner, does not affect the topological nature of the fractional Chern insulator. It occurs at filling 1 over 4s plus 1 with the correct topological degeneracy of 4s plus 1. Importantly, due to the vortex attachment factor, it will be an exact ground state or a zero mode of some pseudopotential expansions up to some power. And we verify this numerically using an ideal Chern 2 band from the monobi graphene at 1/5 filling, which is saying s equals to 1. Here we observe exactly 5-fold degeneracy. So that was pretty much expected. However, more interesting are these translation broken fractional Chern insulators. Basically, we now need to start from a translation broken Slater determinant state, which is a generalized quantum Hall ferromagnet, or as you recall, a topological charge density wave. Once we attach vortices to those ferromagnets, we'll get ferromagnetic Laplace states. The degeneracy of the Laplace state will be greatly enhanced because right now we not only have the Laplace degeneracy of 2s plus 1, we also have the ferromagnetic degeneracy of Ne plus 1. It occurs at the filling 1 over 4s plus 2 because you need to half fill the band to pick out a ferromagnet, and then you fill 1 over 2s plus 1 of that ferromagnet. Importantly, these ferromagnetic Laplace state is exotic because the Laplace topological order coexists with the charge density wave nature of the ferromagnet. The fractional Chern insulator coexists with 2-fold or 4-fold translation breaking. We numerically verify that these states are the ground states in the following way. We project screened Coulomb interaction to the Chern 2 ideal band from monobi graphene. And we project to the 1/6 filling, meaning that we want the 1/3 Laplace state. Then we verify, then we tune the screening length D, and we look at the ground state energy dependence on D, and we look at its scaling form, and it matches with the scaling of Laplace states as predicted. Since the nature of these Laplace states are ferromagnetic, there will be also an emergent SU2 symmetry in the ground state manifold, just like the topological charge density waves at half filling. And to summarize, we have constructed some exact many-body ground states for ideal Chern bands in this case. For Chern number 2, at half filling, we have topological charge density waves, which we understand as ferromagnets. We then study excitations upon these ferromagnets, the most exotic of which is the skyrmion, which, as we see, manifests as windings of charge density patterns. At lower fillings, we get various analytic fractional Chern insulator states through the vortex attachment procedure. And these are analytic fractional Chern insulator states. Importantly, the fractional Chern insulators that we understand do not have to come from the vortex attachment. For example, we can also understand the 112 state that people found numerically a while back. Also, this procedure works for higher Chern numbers too. It is not limited to Chern number 2. Do you have any questions on this section? All right. So to conclude, we have built a new framework to understand correlated physics in Chern bands with higher Chern number. Using the tool of ideal quantum geometry, we can bridge between a single particle description and many body statements. Analytically, we decompose ideal higher Chern bands into many Chern bands with Chern number 1. Basically, ideal higher Chern bands in our description becomes low standard level multi-layers, but the layers are a little bit twisted. And we construct an explicit SUC action that rotates the layers into each other by a combination of momentum translations and real space translations. Using this analytic decomposition, we're able to construct many exact many-body ground states. These include the topological charge density waves, which we understand as generalized ferromagnets, and various fractional Chern insulators, which may break or may not break translation symmetry. And all of this is applicable to the chiral graphene multilayers. There are some questions that are opened by this work. Theoretically, in the study of higher Chern bands, we can ask, when is the higher Chern band equivalent to decoupled multilayer Landau levels? That is, when is our decomposition into Chern 1 bands orthogonal? More realistically speaking, is our prediction still valid when we have non-ideal quantum geometry, when we have non-trivial band dispersion, and when the interaction has slightly longer range than contact interaction? We believe that our predictions, our predictions will not have qualitative differences because of some numerical work that people did in April. It is also interesting to study the coupling of these ferromagnets to other degrees of freedom. Note that the ferromagnets are charge density waves, and thus it will couple to lattice defects, such as lattice dislocations and phonons. And the couplings will be interesting. And with that, thank you for coming. I thank all my collaborators, Patrick, Aslam, John, and Ashwin. Thank you very much.
Thank you, Junkai. Thank you for a really nice talk. Thanks. Question, comments from the audience? Please feel free. Any comments? Please feel free. Please feel free. Maybe let me add something. So it seems to me the discussion is more like a systematic understanding of this higher Chern bands. So this is independent of a material, so anything, just a understanding of the wave functions and understanding of the decomposition you propose. Are there some are there some additional advantage of thinking this way? Maybe help us to understand other phenomena. For example, also in the materials, does this approach give us some advantage? Maybe you already say, but you can also recap again.
Yeah, sure. One thing that let's see. Probably let me say the following. So, for example, if you look at half-filling of these Chern 2 bands in real materials, you also get these charge density waves, and realistically, you can probably develop some Landau-Ginzburg theory on this, on this ferromagnetic manifold, and make realistic predictions on that. I'm not sure if that's what you want.
I think Juven might be asking, just for you to recap, that these twisted graphene multilayers, they host these ideal Chern bands, and we like Junkai and us developed this formalism in order to understand these systems, but as a byproduct, it turns out it's also a systematic study of any system that gives rise to these bands.
Yes, and what are the things you can now say for this twist graphene multilayers? Like what are the statement independent of your formulation? I guess. There's something.
Yeah, right. So for example, in these twisted, for example, monobigraphene, you have not only just one single ideal Chern 2 band. You do not only have one single Chern 2 band, because realistically, it's not that ideal. You firstly need to get rid of the Valley degrees of freedom and the spin degrees of freedom. So let's say we get rid of that by fully filling 3 of the 4 bands. And then basically our predictions make sense at 3 plus 1/2 of the filling of this system. You will get topological charge density waves, which importantly people have discovered. And probably at 3 plus 1/6, you will get these ferromagnetic Laplace states, which you can probe by observing both the charge density variations and fractional Hall conductance, something like that.
Okay, thanks. Thank you.
Thank you.
Any other comments? It's your last chance. If not, let's see. Yeah, we should thank Junkai again. People can still stay to ask questions if they want. Thank you very much. It's very nice, impressive. Thank you.
Thank you.